No, some of them were pretty bad. Like this one? This one? You finished the lab? Nice.
Well, I'm gonna do them, and then we'll talk about them.
I don't think I finished the lab.
Oh, it'll just all be. I'm just kidding. I'm sure there's stuff on here. Honestly, read it was okay. Not a problem. But I reread chapter. Now I know.
Did you do your percentage? I got 90%. Oh, those are no names.
Well, I'm gonna use.
Labs.
Yeah, so if you turn in your, well, it's that Mendeleev periodic table lab, but you don't have a grade.
Ah. I'll grab this. Are you doing a fill out on Thursday again?
Yeah, I told you.
Oh, yeah, huh?
Is it because I wrote a novel? Or should I just like, I don't want to read this? Probably.
I was also generous, because this one was a lot of like effort and like explaining what you did, so.
So no, you didn't do a good job. She was generous.
No, you did a good job.
I feel like the theory that you just didn't want to read it all is probably the most accurate, but I also don't blame you for that. So I don't know why you don't want to turn the paper and read where my arrows are going.
Stick up on you. I can read pretty fast, so.
Yeah. Sadly today I cannot, so, because I have to get, how's anything this afternoon, and I have to like, yeah.
Ooh. Dude, I'm just doing so good on these labs.
I'm really surprised, I'm like, oh.
You feel better?
Yeah. But no. Do we need calculators today? Not a math at 8. But I'm working.
I don't think we need calculators.
Okay, good. So I can't find mine. I don't know what I did with it. Home slabs. They're probably not. Like, even if I study room again, then we should go. Were you out?
Oh, you found?
Not that one, but this one. This be mine.
Okay, let me. And what was the score on it?
19 out of 20. Make sure I pick the right one with the biggest score. I'm no dummy.
Oh,
Do we need
you
these
can
today?
keep it now.
Okay. Do we need these today?
Yes.
What'd you do?
chapter 6 homework?
Did you do it electronically or paper?
I just didn't see it. I finished chapter 5 homework.
Oh, I probably just haven't updated the grades because I have like a stack of random homeworks that I haven't entered, but.
Oh, no, I was asking if we got a chapter 6 last
Oh.
week, or was that chapter 5?
Yeah, it was chapter 6 and 7. Is this?
Nope, didn't get it.
I could get you one lab. Do you have lab today or?
Thursday.
Or I could
Yeah,
get you one
I
after
could print one
class.
off. Yeah, it's no
Okay.
big deal, yeah. Also it's like chapter A, B, C reading. What is that?
They're the Macquarie inner chapters. I think I posted a link.
On the, okay.
Yeah, there's like an electronic link to the chapters. I can go over it in class.
Yeah, I just didn't know. I was like, I don't see this or anything, so.
Last week?
Like 3 years ago, maybe? I don't really know.
Maybe I just put the link. Maybe I didn't put a
It's
link.
just based on how many little. The shape is based on like how many lone pairs you find.
The cold.
And like you fixed which way it bends. Those are just silicone.
I've even told Mary, I was like, that's our Did you guys dress up for Halloween? No. Do I? I did run a I think I did a really good job at running a lot. Good job. Thanks. I did a great job. They're pretty fun.
Yeah.
So, let me pull up the specific example. There was one that has a bunch of bonds, and I just wondered how we would know. So like, carbon monoxide. Is a carbon and an oxygen triple bonded? How would we know that that would be a triple bond?
So this is a good one
Okay.
to start off on, because it is tricky. So you wouldn't know. So start off by drawing, see if you can draw any other structures. So there may be other resonance structures. And then also analyze this, and then we'll talk about it and whether this is a good structure or not.
So we can use other ones if it seems like it works.
Oops. Also, if you're in the chat, just say hello, so I know you're there. So do we get another Lewis dot structure for CO, or maybe criticisms of this one? So what's something odd about this structure? Let's just start with that. What's odd? So the octet rule is satisfied, so that's okay. But did we check out our formal charges?
Well, I mean, you could see even from the triple bond that carbons don't have an extra electron, right?
Yes, and then what is carbon's formal charge then? So you're on the right idea that it's got something extra, but that'll come out in the formal charge. So what's the formal charge on carbon here? What'd you say? So -1. And then what do we get for the formal charge on oxygen then? Do we remember how to calculate formal charges, by the way? Sorry, what'd you say?
-1.
For oxygen?
Yeah.
So double check it. So let's remind people of our formula just in case. So it's number of our valence electrons. So remember, just grab that from the periodic table. Then minus the number of electrons, so individual electrons, and minus the number of bonds. So what does that give you for oxygen? So +1. And so what's the funny thing about this?
They cancel each other out.
So we want them to cancel out though. So the CO is neutral, so that's good that they cancel. But what's the most electronegative element out of these two? So oxygen. So we would expect the oxygen to be carrying the negative charge, and it's not in this case. And so you could try to draw something better. So did anyone come up with other structures? I mean, you could try, we just made this a double bond, then we would put all the electrons on oxygen, so I just moved my triple bond over to oxygen. But of course, what's the problem with this structure? So now carbon only has 6 electrons, so not satisfied by the octet rule. So this is not the greatest structure. So even though we have our formal charges now minimized, so carbon has a 0 formal charge, oxygen has a 0. The octet rule being satisfied is not that great. But then what's really cool, so if we go back and look at this structure, so this has to be kind of our preferred better structure. And again, on an exam, I wouldn't necessarily mark you wrong for this one, as long as you point out, like, carbon is deficient. So as long as you analyze your structure and say, okay, carbon's deficient, but the main thing is you want to have 10 electrons, right? 4 from carbon, 6 from oxygen. So you have all 10 in their total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's okay. You're at least showing, plausible structures. But then what's cool, we can go back to the structure and we can find out that CO, if it reacts, it actually attaches at the carbon here. And sometimes it could also react at the oxygen, but most commonly, so if you're talking about like a cobalt or metal carbonyl complex, and you can, now this is like going into carbonyl chemistry. Let me pick something simpler. That got too complicated. So nickel carbonyl would be like this then. So this is nickel tetracarbonyl. And so again, it attaches at the carbon, which is kind of hinted to us by this weird structure here. So the negative charge is being carried on that carbon. So when it reacts, it will attach at the carbon. So those lone pairs are contributing fully to this bond to nickel. And just a fun fact about nickel tetracarbonyl, you would not want to work with this. So this is like a nice fuming liquid, but the fuming liquid, so it's extremely dense, so a regular fume hood would not be able to suck up the nickel tetracarbonyl. And then this is of course toxic, since if you inhale it, it would plate nickel potentially in your lungs, and of course CO poisoning, so not a good thing. So highly toxic compound, not generally ever used. Excellent, so that was a good warm-up on CO. Any other questions? Welcome in the chat. I see everyone there. And so just a reminder, before we get back into chapter 7. So just a reminder, I'm wearing my nice fluorescent shirt today to remind you all about registration. So registration is open. So I don't know if you guys have checked it out yet. So the class times for this class have been officially changed now, so it should be hopefully not conflicting. So the new class time is going to be 11:30 to 1 p.m. And then I moved lab to Tuesday from 1:30 to 4:20 p.m. and then keeping the recitation on Thursday, so right after. So that would be 1 to 1:50 on the recitation. And so just sign up. There are more of you than there are lab sections, I believe, but if all of you sign up, I assume we would just open up another one. So just sign up ASAP, so then if we do need to open up another lab section, we can figure that out ASAP. And it would probably be Thursday after recitation, just tentatively planning if it comes to that. So again, register. And then I said that I would offer bonus points, and so I will do that in this class. But we'll do bonus points for several scenarios. So I don't know if anyone's graduating, and I don't want to leave anyone out. So if you register by December 2nd, so that's our last day of the quarter, I'll add bonus points. And if you can't register, so let's say, you're graduating, you're transferring, just write me a note or something of what your plans are. Yeah. So they want people to sign up early so we know, like I said, especially for this class, because I don't remember what our exact number is. I want to say 36-ish, but they only have one lab section right now. So I'm expecting if everyone signs up, then we need to open another one. So that's why I'm encouraging people to sign up now so that we know, even if you're on the wait list, then we'll be, hey, we need to open another section. Yeah, like for winter quarter.
In general.
The time for 11:30 is changing like next week or this week?
Oh, sorry, for next quarter, for winter.
Oh, okay.
Sorry, there's been some drama with, because our usual class time conflicts with some of the calculus classes that people are in, and we're also limited by like the biology classes. So I'm just trying to keep it in that window. So that's why I'm letting everyone know what the time is. If it doesn't work for somebody, let me know ASAP. We could try to find another time, but hopefully this is the time that doesn't conflict.
Will you know when you register, or will you tell you?
Yeah, you would email me when you register, but I can see when you register on the wait list. But yeah, definitely just email me for your bonus points. And like I said, if you are transferring or something, graduating, just let me know as well so you can still get your bonus points. So I want to make sure everyone has the same opportunity. So does that work for everybody in getting bonus points?
Yes.
So let's,
One more question.
Oh, yeah.
For the winter term, for the new times, is that for like the next chemistry one?
yeah, so this
'Cause I
would
thought
be,
that one was only, they told me that one was only on for like spring.
which one? Because we do the whole series, so this quarter is the 221, next quarter will be the 222,
Yeah.
it'll be lab lecture recitation, and spring's 223, same thing, lab lecture recitation, and the same courses are offered on both campuses, so there's no trailing series for better or for worse. Did that clarify?
Yeah, I was just confused because the way the advisor was telling me like this class was only offered like in the fall and the spring is supposed to be in February. I was like,
Yeah. Yeah, because 221 is only offered fall is probably what they were saying. 222 is only winter, and 223 is only spring. And I don't quite like that we don't offer a trailing series, but given that I'm the only full-time chemist, we only have so much capacity. All right, other questions, comments? So let's take a look at where we're going for the rest of the chapter. So I don't like the order that we teach it, but for reasons that you don't need to know, so just behind the scenes stuff, I haven't been able to change the way we teach it, since that's a lot of bureaucratic process, because I would change the entire series, which screws up some people. And so it feels kind of hodgepodgey to me. So I don't really like the order that we go in. So the goal is we're going to finish up chapter 7, so practicing a bit more with these polyatomics. And so I do have, I'll pass out this polyatomic ion sheet so we can help. And then I printed out this Vesper and shape page, but I realize now it was kind of premature, which is why I don't like the order that we go in. So I think we're teaching shapes second quarter, which again, I would not do that normally, but that's the way it's been taught, and that's the way it is going right now. So I'm going to hand out the polyatomic sheet. I'm going to leave the Vesper sheet. If you want one, go ahead and grab it now. It may be helpful for drawing stuff, but we're not officially covering geometry until winter. All right, so let's finish up chapter 7 and talk about these polyatomic ions. So we were looking at least at a few of these polyatomic structures. And so we said for our bookkeeping that we have to make sure that, of course, the overall charge gives us what our polyatomic charge is. And then let's also go over naming these compounds. So let's say we wanted to name we have this compound. And so anytime you see our polyatomic, we know that our polyatomic, again, are covalently bonded. And they do have some sort of charge. And so, of course, I handed out the handy-dandy polyatomic sheet. And so anytime we're naming, so the first thing we do, we need to find, well, what is NH4? And this sheet has the same ions on both sides, but they're just kind of alphabetical, either by their name or by their little letter symbol. And so if you look, you can find NH4. And so what's the name of this? So ammonium, and then excellent job. So the ending is just like we've been doing before, so it would indeed be phosphide. And so let's say, let's go in reverse now. So if we were given potassium dichromate, so take a minute or two, find dichromate on your polyatomic. What's the charge? How many potassiums do we need? So does someone want to give me either a formula or what is dichromate? So Cr2O7, and then what's the charge on it? So -2. And so looking at this, so now I'll just put my potassium here, and how many potassiums do we need then to balance out that -2? So I see so 2. And I'm watching the chat as well for answers, so then I'm just going to rewrite it so it doesn't have a charge. So K2, and then our chromate, so Cr2O7 is our formula. Let's try another one. So iron. So how would you name this one? Uh,
CCN?
Yeah, sorry, these are parentheses, and then that's a CN.
Oh,
Try to redraw it.
I thought there was two Cs.
Do you have a name for this one?
Would it be iron tetracyanide?
So, I like the iron, but then what do we do instead of using like the tetra? Yeah, so I see, heard someone whisper Roman numerals.
So is it iron 4 cyanide?
Yep, so iron 4 cyanide. Let's do another one. So tungsten 2 phosphate. Do you have a formula for this one?
That's okay, no, you're good.
W3 and then, so what's phosphate though?
PO4.
So PO4 and then probably 2 of them.
Yeah. Oops, wait.
So-
This is, yes, just joking.
So tungsten 2 plus, so 2 times 3 is positive 6. Phosphate negative 3 times 2, negative 6. So checks out.
But phosphate on here is PO.
Yeah, PO4 3 minus, right?
Okay, I see.
And then you could do tungsten 2 plus, do the swap trick.
Yes. Thank you. I had to see that for a second.
All right, let's do a little bit more practice on our structures. Let's try another one. Let's try a different one. These are slightly repetitive. Let's try azide. That's a fun one. So azide is N3 with a negative charge on it. So azides tend to be pretty reactive. And see if you can draw your Lewis dot structure. And I'll give you a hint, it's not a circle or anything.
Terrible that is like stacked on top of each other, like all of them. Oh, yeah. But, is that what we're doing now too?
Yeah. I was looking.
Like all five of them are like,
There's only 3 nitrogens.
yeah, all three of them are just like
Yeah, I think kind of.
a link. I don't know how to explain it.
I think it's too many. Too long. It's probably close. Let's see what kind of structures. So how many electrons do we have in this entire system here for N3?
Seems to be 16.
So N, so we have each nitrogen is 5 times 3, so 15, and then our negative charge, so 16 electrons total in this system. And so I saw some structures. I saw something of like double bonds of nitrogen in the middle or something. And let's see what that leaves us. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that what other people got from their structure? And so let's put some formal charges on here. So what's the formal charge on this nitrogen? So -1. What's the formal charge on this nitrogen? So +1. So 5 minus those 4 bonds, so +1. And then this last one, so it should be the same since they're symmetric, but what is it? So -1. So this is good. All our charges balance out. So we're left with an overall -1 charge. That's what we started with. And then the next question, can we really do anything else to eliminate this charge? And the answer is, not really. So you could, try to move one over, but then nitrogen would have way too many. And nitrogen does not tend to go hypervalent. So I'm just drawing this of kind of what's wrong with it. And so 10 electrons, so nitrogen does not go hypervalent. At least it doesn't tend to. So this is not the best structure, still okay though. So you've at least minimized these formal charges. We'd still have a -1, but then you'd want to, again, note on an exam, hey, nitrogen is 10 electrons, so probably not the best structure. And you're more than welcome to draw both of them, again, showing what's going on. So this is probably our best one. We have the octet rule is satisfied. And so what can you probably guess about this compound? You think it's reactive, not reactive? So reactive, and you can get that sense you have a negative, a plus charge, and a negative charge. So it's going to want to react, so this nitrogen's going to want to bind to something. And either nitrogen, really. And so this is not too dangerous, but then azides can quickly become explosive, so like super nitrogen compounds. And so this is a fun blog if you're ever bored. So it's by this chemist, Derek Lowe. He's like a very experienced organic chemist. And he always has funny things. And so on his list of things he will not work with is azides. And basically they look like this. So a bunch of azides now on steroids. And these things get very explosive. And so you can read the blog, but essentially they're extremely hard to work with. So even just measuring them, transferring them, they can explode in your hand. So explosion chemistry is pretty hazardous these days. And that's in Munich where they do this. So let's do the sulfate, so SO4 2-. So draw your structure for this, and then don't forget any resonance structures. See if you remember what are resonance structures. how are our sulfate structures looking? So how many electrons total are in this system? So 32. So it should be 6 from the sulfur and the 4 oxygens, so 6 times 5 is 30 plus our 2, so 32. And then how many bonds do we have to the oxygens? So we can assume sulfur's in the middle.
Isn't there a bond on each side connecting the oxygen?
Let's just start bond on each side. And so if we do that, so fill in for our 32 electrons. And so this looks like a good structure. Octet rule is satisfied, so let's put in some formal charges. So what's the formal charge on the sulfur though? So +2. And then what's the charge? So all these oxygens are the same. So what's the charge on it? So -1 for all of them. And so that this is good. So this cancels out our +2 and these two cancel, so leaving us with an overall -2 charge. Now could you draw other resonance structures? How else could you draw this? How can we minimize these formal charges? So what happens when we see a negative and a plus charge next to each other? What can we try to do? So we want to cancel it, so then how are we going to cancel it? So let's move a bond. And so it doesn't matter which one you do. So we could take these 2 electrons, put them into a bond. We could do the same with these 2 or any other side. And then we want to draw our new structure. And so you want to use these double-headed arrows. So this is a resonance structure arrow. So showing that they're just electronically the same. We're just moving electrons around. And so now just draw your new structure. So on an exam, you would want to draw, if you have resonance structures, as many as possible. So negative charge is still on these oxygens. And so how many total electrons do we have on sulfur though? 12. So 12, and so you want to note that, so 12 electrons on sulfur. And this is okay though, so sulfur can go hypervalent, so it's past the second row there. So that's fine if it's hypervalent. The oxygens are still obeying the octet rule, so that's fine. And then we just want to draw, again emphasizing that it doesn't matter where these double bonds are. So rotate them around, draw their other Lewis dot structure. So again, write your formal charges. Indicate sulfur has 12 electrons total. And you can keep going. Again, just drawing all the different forms. So again, doesn't matter which 2 oxygens have the double bond.
So how would we know which
So it's anything below this row.
Which I would know if I had done the reading.
Although I don't know, since we go in such a scrambled order.
It was definitely in either 6 or 7, I just can't remember which one, but as soon as I asked that, and you said, it's anything below, I was like, oh, it was in the reading.
But yeah, it's just anything below here. And I think I've already ranted that, no, they're not invoking d orbitals, but we are not doing MO theory until winter quarter, so we'll revisit that later. So yeah, anything here can go hypervalent. So phosphorus and sulfur, they tend to go hypervalent a lot. And I was just finishing up, hopefully drawing all the permutations.
So is there a maximum number of electrons that a hypervalent atom would accept?
Trying to think. So like there's xenon tetrafluoride. And then xenon has 2 lone pairs of electrons. I'm trying to count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Seems like they tend to max out at 12 generally. But that being said, there's probably like some monster of a compound. And then to further answer your question, for like metals, like transition metals, they tend to go 18. But we're not looking at transition metal compounds. And they're also counted funny. But all right, how are we feeling on these structures, drawing our Lewis dot structures? And then, the last thing I wanted to say about this resonance structure is, again, this is the average of all these structures. So if you could just like computationally imagine, taking this structure plus all 4 of the resonance structures and kind of merging them into one 3-dimensional electronic mapping, that's what basically computational chemistry is giving you. And so you can tell the electron density is located around the oxygen. It's just spread around, rotating. And then we can kind of guess the bonds, what we might expect, again, from computational chemistry or from a crystal structure of this. So we have 1, 2, 3, 4, 5, 6 bonds shared over 4. So 6 over 4 gives us our bonding order. So about 1.5 bonds. And so we would expect our bond length to be not quite as short as a double bond, but definitely shorter than a single bond there. This would be our bond average. Oh, let's do one more, because I forgot we didn't touch on radicals, and we should at least touch on radicals. So try to draw the Lewis dot structure for NO. You're going to notice a problem right away. So how many total electrons do we have in NO? 11. And so right away, what's the problem with 11 electrons? So it's an odd number. So this is telling us this is some sort of radical species. And a radical just means you have one unpaired electron somewhere. And so let's just, so what do we get for the structure of it? Double bond, triple bond, single bond. So if we do a double bond, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that what people got? So something like this. And let's see. So octet rule is satisfied on oxygen. And then we have this weird 7 rule, but again, it's a radical, not much we can do with this. Formal charges. So our formal charges, though, are minimized, so we don't have a formal charge on oxygen. Nitrogen is also 0, so that looks good. Is there any other way we could arrange this structure? So probably not. Again, if anyone has anything. So this would be our structure. And again, we can tell that this is probably going to be reactive, since this is going to want to make a bond. And so NO is pretty important in like radical atmospheric chemistry. And so you don't generally want radicals, but if they appear, obviously you can't avoid them. Right. How do we feel about chapter 7? So now we're going to switch gears, and we can always come back to chapter 7. So there's kind of a lot in there. And so now we're jumping to chapter 10. And so chapter 10 is just now how do things react, basically what types of reactions are common. And so now let's at least start looking through these types of reactions. And so the first one we're going to discuss is the synthesis combination reaction, and sometimes you have the additional combustion reaction. So in this case, this is just solid carbon plus oxygen gives us carbon dioxide. And so the general form for the synthesis combination is you have two things, so A and B are combining together to make one product, C. So you should have less products than you do reactants here. And then additionally, so let's put up another. So if we had like sodium plus chlorine, so that gives us another example that's not a combustion. So these all happen to be combustions, or the first two. And so these first two are special cases of combustion as well. And so you can tell that by the addition of oxygen. So we're burning something with oxygen. And so if you identify it, you also want to add combustion for these two. So same thing with this reaction below. So this would be iron rusting. So 4 equivalents of iron plus 3 equivalents of oxygen combine to give us 1 iron 3 oxide. And so again, this is just another example. So just as long as it's two things coming together to make one thing, that gives us our synthesis or combination reaction. Let's skip this for now. Yeah, I forgot your book goes in like a hodgepodge order, so I don't like it. And so now your book kind of just wants to emphasize the different reactions that they do. So this is group 1 and 2, metal oxides and water. And so if you have, so this is sodium oxide. So this would react with water to give you sodium hydroxide. So same thing with barium oxide. So all these metal oxides will react to give you the hydroxide form. Now let's just go back to this page. So we saw it with the lamp demonstration, so think back to the light. And so all this is saying is ions in solution, how they dissolve. So going over this again, so now we're understanding more and more what's going on. So the water we know is polar. So there's its 2 lone pairs. And so we see in our diagram here, our positive cation is oriented in the center then of a bunch of oxygens. So they're all pointing towards the cation. And so those lone pairs would be oriented right towards the cation. So that's what's allowing for the dissolution of our sodium chloride in this case. And of course, polyatomics, again, we saw that and had that emphasized when we drew our structures. So we're seeing that they're charged ions that are held together in solution. And so that means, right, that sulfate is hanging around as a sulfate ion. So there's a representation of it, sulfur in the middle. You have all your oxygens. And so just like we drew our sulfate, so we drew our sulfate with our negative charge on the oxygens. And so if we go back to the diagram in solution, so these are going to have your partial negative charge on them. So that means the water is going to orient the partial positive side of the hydrogen towards that sulfate. So again, allowing for it to dissolve there. Then looking at magnesium, so of course magnesium is a cation, and so all the oxygens are oriented towards the magnesium. So of course opposites attract, and so you can see that just reflected in that orientation. And so all this is saying is a lot of these polyatomic ions are oxyanions, so we saw that with like, you have phosphite, phosphate, sulfite, sulfate, and all those just contain different number of oxygens. And again, this is just kind of naming trends. So we see that nitrate has another oxygen, so NO3, -1, and this is the more common one anyways. So there's a ton of nitrate salts for like iron, obviously nitric acid, so all that is from nitrate. And then NO2, -1, is nitrite with the I, so one less oxygen. So same thing with sulfate and sulfite. So sulfite, SO3, 2 negative, but you'll mainly see sulfate in practice. And so there's other versions too. So again, refer to your chart to help you. And so if you have hypo, this means even less. And so you can see this in the chlorite family here. So you have hypochlorite, which is just Cl with 1 oxygen. Then you have chlorite, chlorate, and then perchlorate, which means more than, and so that would be ClO4 -1 with the perchlorate. And so bromine does the same thing, so hypobromite, then bromite, bromate, and perbromate. So again, I would just refer to your chart, keep your chart handy. They should all be there so you can see them, the bromates, the chlorates, all on your chart. So we went over naming. And so just a little preview. So now we can also say why do acids dissolve in solution? What is going on? And so anytime you have an acid, let's insert some space here. And so this would be for a strong acid. And so a strong acid, let's first define, well, what is a strong acid? So a strong acid just means that it completely disassociates. And so some examples of that would be HCl. So it would completely disassociate in solution. Nitric would do the same thing. And so in comparison, a weak acid, it would still disassociate, just not completely. And so one example would be HF. And so for anything that's weak, I would go ahead and use this double-headed arrow. So notice a strong acid, I use that single arrow saying all this is going to completion. But with any sort of weak acid, so HF, vinegar too, so that would be acetic acid, they have this back and forth equilibrium. So they do disassociate, but then they would go ahead and reform potentially. And so now the preview that your book is giving you is, well, what happens in solution? And so the first thing, so we said that a strong acid is going to completely disassociate, but then the problem is you formally can't just have a little hydrogen floating around. And so what actually happens in solution is this would be instantaneously taken up by the water. So action should start at the electrons. So our lone pairs on our water would go ahead and attack that hydrogen right away and then form our hydronium ion. So this is just water with the extra hydrogen, so H3O plus. And so anytime you see kind of H plus in solution, it is equal to H3O plus. So this does not actually exist.
Can you say that one more time? Anytime you see a B plus in a solution, it's
It-
actually the H3O?
Yeah, it's just chemists, I always say chemists are lazy, and so they usually won't bother writing out the whole hydronium, but H plus and hydronium are used very interchangeably. And again, the only reason why that is because it just would not exist, because as soon as the water sees it, it's going to attach it to it right away, so it does not have a chance to live as a solo H plus ion. And so the same thing can happen with our organic alcohols. So here's our carboxylic acid group. This H is prime to leave. And so you have some resonance here, so that's why it makes it favorable. And so again, same thing. Water is going to come along and pluck off the hydrogen. That means that the electrons in the bond go back to the oxygen, so that's what's shown in this product here. And of course, they just wrote H plus instead of the hydronium, but that's H plus, so H plus would not just fly off by itself. And then we have our anion here. And so this is a little bit beyond the text, but if you're thinking about OCHEM, you want to think about resonance structures. So this is extremely stable, this group, since we could move these electrons down into a bond. Carbon can't have 5 bonds though, so that would move these 2 electrons back up. So giving us this resonance structure. And so all that does is stabilize that negative charge across the two oxygens here. So this is extremely stable. You may also see this represented like something like this. And so this is kind of the shorthand form of that. So these little dots showing that there's a half bond there. So basically this resonance structure that the double bond's going back and forth between these two. And then that negative charge again is just across there. And so these are just some acids. Don't want to go too much into this. So these would be strong acids. So acetic is a weak acid. Citric is probably a weak acid. Weak. And then so some of these multi ones, so phosphoric, and this will come later. But we'll also learn that these dissociations, so this first one is strong to make H plus H2, PO4 minus. So this would be strong for phosphoric acid, but then the subsequent dissociations would be weak. But we will cover this more like second and third quarter. Again, this is just kind of a preview, at least letting you see, okay, acids do dissociate. This is why they're making H plus ions in solution. That's what we really want to get from this. And so more things from this chapter. Again, this is where I feel like your book is a great hodgepodge of information, but at the same time, it's a great hodgepodge of information. And so it wanted to throw in there in this chapter the characteristics of acids. So if you've had like a lemon, you probably know what an acid tastes like. So they would taste sour. So you know what vinegar tastes like too. If you drink wine or something, like really soury, bittery taste. Again, they produce the H plus ions, and we'll later learn, or we're starting to learn, that acids neutralize bases, and we'll go into the salts. And acids, of course, react with many metals to produce hydrogen gas, so we've seen that when you dissolved your little strip of magnesium. And so meanwhile, just to compare, so base solutions taste bitter and feel slippery. So probably don't want to taste any bases like soap, but you can definitely feel how soap feels on the hand. And then bases also produce hydroxide ions. So just the simplest form, of course, they would dissociate, and that's where you get your hydroxide. So just dissolving ions in solution. So next type of reaction. So first we did synthesis, two things coming together. Now let's look at the opposite. So now A goes to B plus C. So now we have more reactants and products. And this can be any decomposition reaction. So I focused on this calcium carbonate since we've looked at this. So this is what happens in the ocean, and it would break down to give you CO2 and calcium oxide. Any other examples of decomposition reactions we can think of? do another kind of common one. So hydrogen peroxide, the reason why it's in those brown bottles is because it'll decompose. And so hydrogen peroxide decomposes to make water and oxygen. And balance it. So that's why it's light sensitive. And of course, you can speed up this decomposition with some sort of a catalyst. Did we do the potato catalyst in this class, or was that my other class? I mix up the classes. I don't know. I'd have to go back and look at your labs. But
Yeah, there was a potato, it was like a little chunk.
yeah, and then you might have made some gas. Yeah, so we did do it in here. So yeah, you can use a potato. So a potato would catalyze a reaction. I think iodine as well, or potassium iodide. So all those can catalyze this reaction. And then we haven't talked about hydrates in this class, have we? So going on with our hodgepodge chapter. So hydrates, it just so happens, so some compounds are formulated with molecules of water, so that means that they would actually be bound to a structure of water, and this would be like intercalated into its structure. And so we would use these hydrate prefixes to help name them. So this is an interesting one. So looking at this first example, so we would just name it calcium sulfate. So just normally, so you'd have to find SO4 on your polyatomic, figure out its sulfate. And then this little dot here just means it's complexed with. And then this one's odd because it's with half an equivalent of oxygen. So all this means is for every 2 molecules of calcium sulfate, there's 1 molecule of oxygen, again, intercalated somewhere in that crystal structure where it's part of the compound. And so in this half equivalent, you would use the prefix hemi. So this would be called calcium sulfate hemihydrate. So other examples, so you can see monos 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, and octa 8. And of course, you can go on and on. So this example, so this is barium chloride hexahydrate for our 6 hydrates here. Copper, so this is another one that's complex, so copper sulfate pentahydrate for those 5 oxygens. And so just as like a little side note, so you might see so how would you name this one? So what would be the name of this compound? And then, so I like most of that, except what little part are we missing? The Roman numeral. So don't forget your Roman numeral for our iron variable oxidation state. So iron 2 chloride dihydrate. And then the only thing I wanted to point out, so versus, and you might see this in the literature, they might just use this term, so iron 2 chloride, and then they might say anhydrous. So anhydrous just means no water. And so sometimes you just see that if you're reading a prep, especially if you're doing like a air-free chemistry, they would specify, hey, use the anhydrous version, so you know definitely don't put water into this reaction. And that's very common. So if you were like shopping around online for these iron chloride salts, there are different variations. So the hydrated ones are generally cheaper, since they're cheaper to make. You know, it's not a big deal to make stuff with a bunch of water, but then it's trickier to keep stuff dry, so the anhydrous stuff is usually more expensive, but if you need it, you need it. And you can sometimes make the anhydrous version, so like nickel chloride, for example, you can make the anhydrous one by boiling the crap out of it in a Dean-Stark reaction. I think have I mentioned the Dean-Stark in here before? I'll pull up a Dean-Stark again if I didn't. But this is a Dean-Stark apparatus, this thing here. So you would have your nickel chloride and toluene here, and then you just boil the crap out of it. This collects the water, so you would boil it, you're eventually displacing the water. And then this little stopcock is there, so you can drain out the water if you have like a large amount, but otherwise you just fill it here. The top layer would be your organic solvent, so you'd have to plan this to where your organic solvent is less dense than water. So not all organic solvents are less dense, but then boil it, drain out your water, and then you'd have nice anhydrous nickel chloride in there. And so there's just different preps you could look up if you needed to prepare an anhydrous one. All right, we'll just go ahead. So let's stop there before we go into the other reaction type. So we'll pick up on Tuesday. We'll finish up the single replacement, the double displacement, and talk about the activity series and continue with our hodgepodge of reactions. So Thursday too, come with questions. I know we've kind of been skipping around recently in the chapters, so ask questions if things aren't making sense. If I didn't cover something very well, we can go back and hit it up on Thursday. All right, so thanks again. Thank y'all for being on stream. I'm going to stop the stream, and then I'll see y'all in lab. Oh, I forgot I have homework for you guys. So if you want homework, I'll put it right here. Come grab it. Oh, and then there's a homeless Mendeleev's periodic table. So if you didn't get a grade and you turned it in, check that that's not yours.
So when the equations are written like this,
See you.
so this is kind of new to what we've been doing, right?
Yes.
So this is, I mean, what is the question I'm trying to ask here, Marissa? I guess this is just, it's new, and so when would we use this? When would we just write out the formula?
Oh, yeah, huh?
It depends what you're trying to show. So in this case, what they're trying to show is where the hydrogen is coming from, and then they're showing you like the form after. So this is like kind of electronic bookkeeping in some way. Because they don't show the arrow action, which that's fine, whatever. But what we want to see is, okay, we made 8 plus, but then the other thing is where did those electrons go? And so that's why I made sure to like circle them and show that they go back to oxygen, because we can't just have them like popping off, floating somewhere. And that's really key in OChem, is like where are the electrons?
So why didn't they draw out the CH3?
It's not relevant.
Okay, I think that's also why I'm just confused. 'Cause they
Yeah,
didn't
well,
draw
that's why
that
we practice now, because, yeah, so you know what's relevant, what's not relevant.
Cool.
Upper lab. Thank you. Oh, at least I know yours wasn't the homeless.
Depending on the score, I'll take it.
It was a good score, so.
My name's on the homework.
Oh, yeah.
What was the new homework?
Oh, I put it over there. Huh?
What?
I was wondering, for electric affinity, is that something we're supposed to figure out, or can we look it up? We're not supposed to know.
So you should at least know the general trend.
It's like the trend, yeah. but
Yeah.
not the specific.
No, you don't need to know the values. Like if you were ever asked to calculate it, you'd have to be given the chart or given the relevant values.
Just making sure.
Yeah.
I was like, I don't know how to do it.
And yes, there's still lab at 1. I'm not signed into the chat, so I can't respond. Text, but yes, lab at 1. All right, I'm going to end the stream, and I will see y'all in lab if you can make it. Otherwise, if you can attend the Thursday section, there's room in the Thursday section as well for y'all. Oh, awesome. Glad you're still there. See you in lab if you can make it. Otherwise, see you Thursday. Probably going to end. Oh, were you the homeless one?
Yeah.
Okay. I will record your score and then I'll have the paper back. All right, thanks again.